Thank you for catching me back for question number 15 on the winter 23 midterm review. It says a research team at Cornell University conducted a study showing that approximately 10% of all businessmen wear their ties too tight. Suppose you randomly select 20 businessmen, all of whom wear ties, and you are interested in how many of them wear their ties too tight. So find and or explain the following for this experiment. So if it is a true binomial, it'll have a fixed n. In this case, we do 20 businessmen. Each businessman should be independent of one another. And a success is, in this case, considered tie is too tight. And so that means failure is tie is not too tight. And the probability of success has to be the same for each outcome. So the probability of success is, we said 10%. That means the probability for failure, which is also Q, is 1 minus P. So that's going to be 0.9. And then X is going to be between 0 and 20, because X is the number of men with tie too tight. So we could have anywhere from 0 of the men that wear their ties too tight all the way through all 20 of them. Okay, explain what this means. So it means, what is the probability? So the probability that no more than 5, because we're including 5, so no more than 5 men wear their ties too tight. C, D, and E are just practicing using the binomial distribution, which we've been using. So let's write out the symbols for all 3, and then we'll go to Desmos. So this says the probability that exactly 3 ties are too tight. So exactly is going to be an X equal to 3. And then we've got strictly less than 2. So when it's a strictly less than, in Desmos, we're going to have our minimum 0, but our maximum can't be 2 because we're not including that. So it has to be 1. So we'll go to Desmos and find that. And then E is the probability that at least 4. So in Desmos, because it's at least 4, that's greater than or equal to 4. We're including 4. So now our minimum is going to be 4, and it's going to go all the way up through 20. And it's cumulative because we want to include all of those outcomes. So let's head over to Desmos. And we'll put that in. So here we have the distribution. I'm going to just scale it. So we want exactly 3. So when it's exactly, you don't need the cumulative. So I'm going to click on, there's the 2, there's the 3. So the 3, so letter C, probably exactly equal to 3, is 0.1901. And the next one was less than. So I'm going to click on the cumulative, and it's going to be 0 up through 1. And that is 0.3917. And then E was, this time the max, or the min is 4, and the max is 20. And that is 0.1330, because we have to round appropriately. So it should be 0.1330. And this is what it looks like on my paper. Okay. So questions 16, 17, and 18 are right here. So question 16 says, which of these exam grades have a better relative position? And so we learned that relative position can be measured using a z-score. So we're going to look at Megan had a grade of 82 on her exam. And that test had an average score with all students of 85 and a standard deviation of 6. And then Abby, we want to see which student had a better relative position. Abby had a grade of 56, but the average on her test was 60 and a standard deviation of 5. So I'm going to take you to my paper so we can go over again the formula for z-score. So the z-score is the average number of standard deviations an observation is above or below the mean. So you're taking your observation, that would be Megan's test score, and you're subtracting the average, and make sure that this is done first, and then you divide by 6. Make sure that that's in parentheses. So this would be a -3 over 6 is a -0.5. So she scored under the average by a half of standard deviation. Now, Abby also scored underneath her peers. A -4 over 5 is a -0.8. So if you think about this on the number line, they were both below 0. But here was Megan. Abby was further away. Here's Abby and here's Megan. Abby was further away from her peers, so Megan scored better. Not well, she wasn't above the mean, but she scored better than Abby. Okay, let's go back to the review here. So number 17 says, we have events A and B are mutually exclusive with a probability of 0.392 of A and the probability of A or B 0.653. So we're going to find the probability of A and B, the probability of B, and the probability of not A. So because A and B are mutually exclusive, the A and B is going to be 0. Okay, because they're mutually exclusive. So if I want to find the probability of B, I know the probability of A or B, because they're mutually exclusive, is just the probability of A plus the probability of B. And I know this value, and I know this value. And I want to find the probability of B. So I can subtract 0.392 from both sides and find out that the probability of B is equal to 0.261. And there's no overlap because they're mutually exclusive. Part C says, what is the probability of not A? Well, the probability of not A is the same as the probability of B because they are complements of one another. So that's just 0.261. Okay. So let's go back to the review for the last problem here, number 18. Says the probability that it snows and the bus arrives late is 0.023. Joseph here's the weather forecast, and there is a 40% chance of snow. Find the probability that the bus will be late given that it snows. Okay, so let's go to the paper to work this out. So that we know the probability that it snows, it says, they told us that the probability that it's going to snow is 40%. They also told us that the probability that it snows and the bus is late, the and is 0.23. We don't need to know B because it says they want to know what is the probability that the bus is going to be late given that it snows. Okay, so if we want to find this contingent probability, that would be the probability of B and S divided by the probability of S. And so that's going to be the 0.023 divided by 0.4. And that comes out to be 0.0575. And that concludes the review for the midterm. Reach out if you have any questions.